Video compression is pretty cool. It's what allows you to watch this video right now from across the world without buffering or taking up gigabytes of data. But what if compression didn't exist? How big would video files get? And just how big can file sizes get anyway? This is what I aim to answer today. And while this isn't really game dev related, this is about the other things that I like, which is computer science, math, and explaining stuff. So, how do you think videos get saved? The naive answer would be saving the value of every single pixel for every single frame. However, doing that would be extremely wasteful. So instead, we use compression. I'm not gonna explain how it works because it's a little complicated, but if you're interested, this Tom Scott video explains the basics pretty well. Also, just so we're on the same page, when I talk about kilobytes, megabytes, and gigabytes, I'm referring to the decimal definition, not the binary definition. We good? Alright. So, without compression, how can we calculate the size of videos? Well, to answer that, we need to talk about pixels. So what is a pixel exactly? Well, most screen nowadays uses 24-bit color depth, which means that a pixel can have 16 million different colors. You might be familiar with hex codes that are sometimes used to represent colors. They use a combination of 6 letters and numbers to represent color. This is called hexadecimal. We're all familiar with counting in base 10 and binary, which is base 2. Hexadecimal is base 16, where you need to go up by 16 before adding 1 to the next digit. We go from 0 through 9, then A through F. Why do we use hexadecimal? Well, you probably already know that a byte is made of 8 bits, and a byte can have 256 possible values. Conveniently, a 2-digit hexadecimal number also has 256 possible values. So we use 3 of them, one for red, one for green, and one for blue. This means that to store a single uncompressed pixel, you need 3 bytes, hence 24 bits. Now let's say that our video is in 1080p with an aspect ratio of 16:9. That means 1920 by 1080. Or 2,073,600 pixels. Multiply that by 3 for the bit depth of each pixel, and we get 6,220,800 bytes for a single frame. Now let's say your video runs at 60 frames per second. 1 second of video is now 373,248,000 bytes. And now, let's assume the video is 10 minutes long. That's 373,248,000 times 60 seconds times 10 minutes, or 223,948,800,000 bytes, aka 223.9 gigabytes. Do you understand how important video compression is now? In comparison, my previous video, which was 11.5 minutes long, was 1.5 gigabytes after being exported. Now this is big and all, but I want to do even worse. If we made a video using the highest quality theoretically possible without using any compression, just how big would our file get? Now, although 16 million colors is more than enough to cover the entire human vision, there are screens that can display more than that. Indeed, allow me to present you 48-bit color depth, which is 16 bits per color channel. You could also add to that a 16-bit alpha channel, which would create a 64-bit color depth and offer 18 quintillion different colors. This means that we would need 8 bytes to store 1 pixel. Now, most video formats can't support transparency. Keyword being most. I don't really know how it works, but all I know is that it's not impossible. And even if we don't use any transparency in the hypothetical video, we'll assume that those bits are still there and are simply left unused. Okay, so now let's talk about resolution. Above 1080p, we have 4K and 8K. Why is 4K not 4000 and 8K not 8000? Well, that's because that's about how many horizontal pixels there are, assuming a 16:9 aspect ratio. Which would make sense if it wasn't for the fact that resolution names refer to vertical pixel count. But I digress. Let's say that our video runs in 8K with the super ultra-wide screen aspect ratio. You know those really long gaming screens that wrap around your field of view a little bit? Those can have an aspect ratio of up to 32:9. 8K means that vertically it is 4320 pixels tall. The width of the screen is then 4320 divided by 9 times 32, or 15,360 pixels wide. This means that our video has a resolution of 4320 times 15,360 for a total of 66,355,200 pixels. This means that a single uncompressed image of that resolution and color depth would be 66,355,200 times 8, or 530,841,600 bytes. Now, an image is good and all, but we want a video. 60 FPS was already pretty good, but screw it. Let's go for 120 FPS, which is possible on some video codecs. A single second of uncompressed video at 120 FPS with an 8K super ultra wide resolution with a 64-bit color depth is 63,700,992,000 bytes. But that's not all, because video also contains audio. Uncompressed audio formats have three main stats: channel number, sample rate, and bit depth. We can get the amount of bytes per second by simply multiplying these three stats, then dividing by 8. You probably already know about channels. Mono is 1, stereo is 2, and the home cinema surround sound system up to 10. Sample rate is how many times per second, in hertz, does the frequency changes. And the bit depth is how many possible different frequencies you can have per sample. It's kinda like the color depth from earlier. 24 bits is more than enough for most cases, but of course, some formats allow up to 64 bits. As for channels and sample rate, things get a little extreme. For channel number, WAV files with LPCM encoding allows for 65,535 different channels at the same time, apparently. Similarly,